Let's get started. Um, I think last class we didn't get to finish on all the parts on the backhouse filter design, right? So we mentioned that for a backhouse filter, basically there are different types. For different types, we have to come up with a different design problem. But luckily, most of our problems are mainly focused on the mechanical shaker backhouse filters. So that's just one type of it. Right. So again, we can do a quick recap of our last class. So last class, we mainly derived some equations about the pressure drop. So we mentioned that the pressure drop is dependent on the thickness of the filter material, right? The pressure drop is proportional to V multiplied by D divided by K, right? We mentioned that V is the phase velocity, right? The thickness is the filter material or the particle layer, right? And then K is the permeability. So we also show that for the particle layer, it will basically get accumulated as time goes on, right? So if we get thicker particle layers, then we're going to have a higher pressure drop for the system, okay? So that's why we cannot operate the filter for a very long time. So let's say if you have an air purifier at home, then it always recommends you to clean up or wash the filter maybe after a month of operation, so you don't get the whole thing blocked. Otherwise, you can see basically all the wires, fibers penetrating from the side of the filter, right? So basically that's a leakage. What that means is that the pressure drop is already very high enough on the filter material. So all the particles will try to go from the side of the material to penetrate through, right? So I also mentioned about the three different mechanisms of the backhouses. So we have the mechanical shaker backhouse, we have the reverse air backhouse, we have the reverse jet backhouse. So we mentioned that for these two, for 1 and 2, we have to clean them up periodically or for maintenance, right? For example, for the reverse air backhouse, we have to shut off the clean gas outlet and then flush in the backwash air, right? This is clean air to get rid of the particles deposited on the filter here. And in terms of the reverse jet backhouse, it's just sending a jet of air so it can get the filter clean. So therefore, the maintenance requirement for the reverse jet backhouse is less compared to the other types of filters, right? So because of the cleaning cycles, what we mentioned is that we cannot use just single one compartment for the backhouse filters. We have to use multiple of them simply because if we just have one of them and when we clean that, it means that we have to shut off the entire system, right? So that's why it comes up with the idea of the compartments. What that means is, let's say this is the combustor of the coal-fired power plant, right? We know that there are fire, burning coals, right? And the, say for example, the flue gas will exit from the top, right? And will go through a cyclone or the pre-cleaner that we talk about, right? The air will exit from the top. And then when it goes through the filters, it will get separated into different compartments. And these compartments are in parallel. They're not in sequence, mainly because these filters already have very high efficiency. There's no meaning for us to put a series of filters because it's already 100% of remove efficiency. There's no need to send in the clean air to the next backhouse filter, right? So that's why they are in parallel, and we separate them into different compartments. Let's say there are 4 compartments in the system, right? So the exact number of the compartments really depends on the flow rate of the flue gas, the type of the particles we're dealing with, and also the dimension of the filter bag, okay? So here we also mentioned that there can be multiple compartments of the filter. So let's say, for example, if we're trying to clean this compartment number 2 here. So what that means is that we're just going to shut off this valve here and then let the air to go through the other backhouse filters, right? So what that means is that the velocity or the phase velocity going through the filter media will increase. So also, since we know that the pressure drop is proportional to the velocity, we know that during the cleaning cycle, the pressure in the system will become higher, mainly because we get rid of one of the compartment in the system, right? So that's why we can see this response of the pressure in the system. So this is basically the variation of pressure drop in a compartmented backhouse. Let's say we have multiple compartments, right? Again, similar to that one, right? So let's say, for example, we're beginning from this point where all the backhouse filters are very clean. Mention that the pressure drop and time theoretically should follow a straight line there, but they're not, mainly because the filter media is not uniform there. So it will start with a curve and then increase linearly, right? And then we realize that we have to get rid of one of the compartment, basically shut off a line here, right, for cleaning the compartment. So because of that, the velocity, the phase velocity through the other three compartments will increase, and that will cause a significant increase of the pressure drop. And then we have to clean the compartment for some time, right? Let's say for TC, T clean, right? So we know that the pressure drop will continue to increase linearly. And then after this compartment is cleaned, we put it back in line, and you can see a significant drop of the pressure drop, right? So this simply means that all the backhouse filters are clean again, and then we'll go through this cycle again. So next time we might be cleaning this backhouse. The next time we'll rotate in terms of the cleaning cycles, right? So this really demonstrates that in terms of the backhouse filters, we have to consider the extra or the excessive number of the backhouse filters, right? We have to leave one extra in the system so that all the remaining compartments can still handle that amount of the airflow for cleaning the particles. Okay. So now we come up with the problem of designing the backhouse filters. So we're going to focus most of our efforts on the mechanical shaker backhouse or the reverse air backhouse. Okay. So in general, for these two types of the backhouse, the material for the filter media is quite similar, right? They don't involve very strong materials. It's not like the reverse jet backhouse where you have to inject a high-speed jet into the material. So this type of material will require higher or better strengths, right? The price will become higher. But for these two types of the backhouse filters, we can just use normal types of the backhouse filter media to achieve the job. Okay. So the way we design these problems is first to understand what type of particles we're trying to deal with. Okay. So let's say we're trying to deal with flour particles. For example, we're trying to design a PM removal system for a flour company generating flours from wheat, right? So we don't want to emit a lot of these tiny particles into the atmosphere. Also, flour particles are combustible, right? They're quite dangerous if we directly emit them out. So the first thing we should do is to refer to the table 6.1 to find out what is the filtering velocity for this type of material. So we can find, we actually in the table 6.1, we find a series of different types of particles, right? It can be active charcoal, carbon black, all the way to leather, paper, tobacco, and wood. So for different types of particles, they can have different maximum filtering velocity. This filtering velocity is just the phase velocity we talk about, right? So let's say if we're trying to inject, if we're trying to filter very hard particles, hard sphere solids through the filter media, then the phase velocity or the filtering velocity should be lower because those particles are very sharp, right? They can easily cut open the filter media. But if we're talking about very soft particles, let's say paper or wood, then they don't necessarily need a very low filtering velocity, right? So they're not going to do any damage to the filter media. So that's why we're seeing that for these softer particles, we can use a higher filtering velocity. But for the more hard or the solid particles, sharp particles, metals, right? We should use a smaller filtering velocity. Excuse me, filtering velocity. So we give an example of the flour. So can you find flour particles in the system? Let's just do a very quick quiz. This is even not involving calculations, right? So let's see if we can find flour here. Okay, 10 more seconds. All right, we'll stop here. Yeah, so I would say this is probably challenging your response or challenging your how you can identify some parameter in the table. Okay, so there might be quite many words here, but you can see the flowers here. Okay, so it has a maximum filtering velocity of 2.5. Okay, so we're going to deal with quite many problems looking at the Backhouse filter design. So try to get familiar with this table. You don't necessarily need to memorize it, but at least you should try to identify which particle it is, right? Oh, I forgot to share the results. So most of you guys get the correct answer. Right. Okay, so we find that basically for the flour particles, we can identify its maximum filtering velocity, right? So in general, for any industrial plant, it will give you what is the flow rate, what is the total flow rate of the flue gas, right? So if you know the phase velocity, then you can easily divide the flow rate by the filtering velocity to calculate an area, right? So this area is the cloth area or the filter area to remove the particles. It is quite straightforward, right? We can just directly divide the total flow rate by the phase velocity to calculate the total area that's required by the Backhouse filter, okay? So further, if we know the total cloth area, then we need to refer to table 6.3. So this is table 6.3 to find out how many compartments we need. So let's say, for example, if we find out that the total cloth area is somewhere around 70,000 square foot, right? Then we know that the number of compartments should be between 11 and 13. We can choose whatever number we want here. It can be 11, 12, or 13. It doesn't matter whether it's getting close to 80,000 or getting close to 60,000. You can choose whichever number you want in designing the system. Okay, so this is the total number of compartments that's basically in practical design, how many we need, right? So for example, here, the total number of compartments is 4. So what that means is that the total net cloth area is somewhere in this range, okay? So once we know the total number of compartments, we can start to look into how many filters we need in each compartments here, right? How many Backhouse filter or filter bags we need in each compartment. So what we're going to do is we're going to divide this total area of the cloth, total area of the filter, by n-1. So this n here is the total number of compartments, right? And not n-1 is just considering the situation where we get one of the compartment offline. We were mentioning that compartment can be periodically cleaned, right? So if it's cleaned, they're taken offline. We have to make sure that the filter media can still handle all of the flow rates, all of the particles when one of the compartments is offline. So we have to calculate what is the area of the filter in each compartment, and that is calculated by AC equal to A divided by N minus 1. Okay, so once we know what is the filter area in each compartment, then we can look into how many filter bags we need in each compartment. So that can be done by calculating the number of filter bags. So basically, we need to know what is the dimension of the filter bag. And unluckily, basically, a lot of the manufacturers, they already identify what type of filter bags they need. So they can manufacture. So those parameters are already given in these scenarios, okay? So if we know the area of each single filter bag, then we can calculate how many filter bags we need for each compartment. So in terms of the area, if you consider basically for each filter bag, let's say its diameter is D, the height is H, right? So we know that the area of the filter bag is going to be pi over 4 multiplied by D squared plus pi D multiplied by H, right? So that is the area at the bottom and also the area at the side. So for the side area, that is the circumference of the circle multiplied by H, right? And in general, these Backhouse filters or the filter bags have a very long dimension there. So we can typically ignore this base area here and just use pi dh as the area of a filter bag. So that's why we'll divide this AC by the pi dh to get how many number of filter bags we need in each compartment, right? And then after we get this number, we need to go through some practical design of the compartment. For example, if we find out that this number is, let's say 101, right? So if it's 101, it's a prime number. So what are we going to do? Notice that a lot of these compartments here, they have a dimension here, right? So there are multiple rows and columns of the filter bags in the system, right? So if it's 101, it's a prime number, it means that the only way to accommodate 101 filter bags is just to build a long column of the compartment and then let it be a straight line here. And this is very impractical, right? So let's say if the wind blows over the compartment, and then it's like building a wall, right? So it's gonna fall over. So we have to round it. We have to adjust to find a better number here. Let's say we can round it to 102 because 102 is divisible by 3, right? So 102, let's say, is equal to 3 multiplied by 34, right? And 3 multiplied by 34, that's 3 multiplied by 2 multiplied by 17. So we can basically build a compartment that has 6 rows and 17 columns, right? So it's going to have a shape that looks like this. Or a better way to do that is you can round it, or you can find a number that's 121, right? 121 is 11 by 11. So that's more effective. Or we can use 110, which is 11 by 10. Okay, so we're going to get more uniform size of the compartment. So instead of building a straight line of the filter bags in each compartment. So that is involved with the practical design of the compartment here. And once we have this actual number, so no matter whether it's 110 or 121 or 102, so this is the actual number of the filter bags in each compartment. And then we can use this actual number to calculate what is the actual filter media, because we need to multiply this number by the number of compartments and then multiply that by the area of the filter bag, okay? So this process might sound quite complex here. I spent quite a lot of time going through these steps, but they're actually quite straightforward when we're trying to go through a problem here, okay? So here I'm giving an example on the textbook. This is example 6.2. So it wants us to estimate what is the net cloth area for a shaker backhouse that must filter this amount of flow rate of air and with 10 grams of flour dust. So 10 grams, this is just a unit of concentration. It doesn't matter for the design of the Backhouse filter, but the type of the particle matters a lot. Okay, so this is trying to filter out the flower dust. And also it wants us to specify the number of compartments to be used, right? And also what is the total number of the bags required to set up this Backhouse filter. So let's assume that each bag is 8 feet long and 6 inches in diameter. Okay, so it has basically a 8-inch of height, and then 8 feet of height and 0.5 feet of the diameter, right? So how do we tackle this problem? So if you go through these steps, we can try to look at it one by one. But as we have introduced earlier, what we need to do first is to find out what is the maximum filtering velocity, right? So we have done the quiz earlier, so we have to find out or locate where the flower is in this table here. And we can find out that first, this maximum filtering velocity turns out to be 2.5 feet per minute. Okay, so once we have this flow rate, or once we have this velocity, then we can calculate what is the net cloth area. So that is just calculated by A equal to Q divided by velocity. Right, we know the Q is 40,000 cubic feet per minute, right? And then divide that by 2.5 feet per minute, right? So theoretically, we should use standard units, but here, since the units are unified in terms of the feet, right, and minute, we can directly put in this number here. So the number come out, it turns out to be 16,000 square feet, right? So once we have this cloth area, we can refer to this table to find out how many compartments we need, right? So we see that 16,000 is here, right? We can choose either 4 or 5 compartments. I mentioned that the exact number doesn't really matter. We can use whichever number we want in this compartment here. So we can later also show that you may think that building fewer compartments might save some money in terms of the capital cost, but it turns out that if you use a smaller number of compartments, you have to purchase more filter media to purchase more filter material. Basically, the cloth area will increase. So that's why really it doesn't matter which number you choose. So here, let's say that we choose 5 as the compartment number. Okay, so it can be 4 to 5. Let's choose n equal to 5. Okay, so this is the number of compartments for our system. So now we need to design the details of this shaker backhouse, right? Basically, what that means is that the flow is being separated into 4 compartments, 5 compartments, right? The air will go this way. Okay, so we mentioned that periodically we have to clean this system. So we have to put one of them offline. So that's why when we design the other 4 compartments, when we design the compartments, we have to make sure that the other 4 will have the required cloth area. Okay, so what that means is that when we calculate the cloth area in each compartment, we should divide this total area by 5 minus 1, or n minus 1. So basically, let's say if we take one of the compartment offline, then the other 4 will still have the total area that's required here, right? So this simply represents that mechanism there. So we can plug in the numbers here, which is 4,000 feet square. Okay, so this is the required cloth area in this compartment. And now we can calculate what is the number of the filter bags in this compartment, right? So we're looking at, let's say, for this compartment, we're trying to know what is the arrangement of the filter bags in here. that can be calculated by n equal to AC divided by pi dh. AC is the required cloth area in this compartment, and then pi dh is the area of the filter bag, right? So if you plug in the values for 1,000, pi minus d is 0.5 feet, right? H is 8 feet. So that's basically 1,000 divided by pi, which is 318.5. Okay. So we know that we cannot just use half of the Backhouse, half of the filter bag in this compartment, right? So this is basically similar to the design of the ESP. We have to round it up. So if we round it up, then we have 319. Okay. So is 319 a prime number? We don't necessarily know, right? It's highly likely to be a prime number because it's not divisible by 3. It's not divisible by 2. You can try out, right? So it's not necessarily a number that can be arranged in a compartment very well. So what that means is that if 319 is a prime number, we have to build a compartment that looks like a straight line there. We said this is not practical. So what we do is we'll further increase that to 320. So we know that 320 is 16 multiplied by 20, right? So in this way, we can have a compartment that has 16 rows and 20 columns. So this is going to be a more uniform compartment where we can manufacture both the casing of the compartment, and also it's easier to arrange the columns in the system there, okay? Or if you want, you can also increase that to 324, which is 18 multiplied by 18, okay? So if it's 18 multiplied by 18, that will further save you some cost, because now, let's say if you want to manufacture the side of the panel, right? So you can just manufacture exactly 4 pieces that has the same dimension, because now you don't have to basically design different programs or use different modes to manufacture this system, right? So if you have 18 by 18, that will be even better, okay? So let's say, for example, we choose 320 in this system, okay? So what this means is that this is the actual number of the compartment, actual number of the filter bags in the system, right? So theoretically, when we calculate the 4,000 square foot, that is the ideal situation, right? Because under the ideal situation, we have to use half of the filter bag, but now we're using this new number of the filter bags there. Then the net cloth area will be different, will be larger than this ideal situation, right? So we have to back calculate what is the total number of filter bags and also what is the total area of the cloth. So the way we can do that is first to calculate the total number of the filter bags, we'll multiply by n multiply n by the number of compartments, which is the capital. Multiply by 5, that's 1,600 number of the filter bags required, right? And then if you calculate what is the actual, let's say AA, the actual cloth area, then that's going to be NT multiplied by pi DH, okay? So this is the area of each filter bag multiplied by the total number of the filter bags. And you see that the total area is higher, basically it's larger than the system, right? It's basically larger than the required cloth area. Okay, so this is the actual cloth area, or the net cloth area of the system, right? So basically this is how we can look into designing such a system to filter the particles, a Backhouse filter system, right? So now we can do a similar example, similar problem, except that we change to another set of parameters. Let's say now we're trying to deal with, so I forgot to change this particle type here. Okay, so let's say that we're trying to deal with cement particles. Okay, because we're civil engineering, let's deal with some cement particles. Okay, so we change the flow rate to a higher value, 80,000. And then the dimension of the filter bag also changed from the original 8 feet long to 5 feet long. Okay, so how are we going to deal with the system? How are we going to look at this problem? So the lucky thing for the cement and the flour is that actually they're in the same category. Okay, so they share the same maximum filtering velocity. So because of that, we know that the V again is 2.5 feet per minute. Okay, and now we're having a new flow rate, so we have to calculate what is the area of the, basically the area of the cloth that's required to remove the particles, right? So that's going to be 80,000 divided by 2.5, and we can have basically 32,000 square foot, right? And then we'll refer to table 6.3 in here. So 32,000 is in between 6 and 7, right? So let's say that we choose to use an n number of 6. Okay, so 6 compartments, right? So then we can calculate what is the area that's required for each compartment. So that is A divided by n minus 1. So minus 1 again means that we have to consider the situation where one of the compartments is offline, right? So if it's offline, we can find out that 36,000 divided by 6 minus 1, that's 6,400 square foot. Okay. So then we can calculate what is the number of the filter bags in each compartment. So that is AC divided by pi dH. Pi dH is the area of each filter bag, right? So that is 6,400 divided by 3.14 multiplied by 0.5 multiplied by 5. That is 815.3. Okay, so again, we need to find a number that's divisible by the, basically have a practical length and the width for this compartment, right? So we can first round it up to 816. And actually this time 816 is divisible by 3, right? We can separate out, actually it's 3 multiplied by 16 multiplied by 17. Okay, so further you can separate the 2 outside, so that's 2.8, 2 multiplied by 8, right? So you have basically 24 multiplied by 34. Okay, 2 multiplied by 17, 3 multiplied by 8. You have this arrangement here. Okay, so in this way, you can have a somewhat more practical dimension of the filter bag, right? It simply means that there are 24 rows and 34 columns. Okay, so we mentioned that we can use two different types of the numbers here, right? So it can be either 6 or 7, right? So let's see what's going to happen if we choose 7 as the compartments. Okay, so we haven't finished up for this problem here. So this is step number 6, where we find out the practical design. As 7 is to calculate the actual filter area. So the actual filter area will just be A equal to the filter bag pi dH multiplied by n, multiplied by the capital N, which is number of compartments. You have 38433.6 square feet. Okay, so this is for the situation where we choose n equal to 6. And if you calculate for n equal to 7, so probably I should just skip the calculation here. You can do that offline. So what you can find out is that the maybe I'll list out the answers. So the AC is 533.3 square foot. N is equal to AC divided by pi dh, which is 679.4. You can round it up to 680, right? And 680 is 20 multiplied by 34. Okay, so you can use that as the practical design. And then finally, when you calculate the total class area, pi dh, n multiplied by capital N, that is 37366 square foot. Okay, so here I have to circle out these two numbers. Okay. So this calculation means that although we use more number of the compartments in the system, the total class area not necessarily higher. So actually, it's smaller. The class area is smaller compared to the 6 compartment scenario. Okay, so that's why when we design the system, we don't necessarily need to consider which number we should use here. You can pick whatever you want for the practical design. Okay, so this is all for the design of the shaker backhouse. We can also mention a little bit about the reverse jet backhouse or the pulse jet backhouse. So we mentioned that the pulse jet backhouse typically requires a stronger material for the filter, right? So what that means is that the filter or the phase velocity can be actually higher compared to the mechanical shaker backhouse. So we can indeed compare their orders of magnitude. So here, because it's this table here, so the maximum filtering velocity for the pulse jet backhouse, for a lot of these particles, let's say for flour here, you can see that the phase velocity is much higher compared to that 2.5 feet per minute, right? So basically, if you have a higher velocity, if you have a higher maximum velocity, see it's going to change. It's going to change the net class area, right? Basically, you have a higher velocity, then you're going to save some material for the filter bags. So basically, the system, the volume of the system for the backhouse will become smaller, mainly because we're using more expensive materials to filter out these particles, right? So compared to the shaker or reverse air backhouse, where you can only use some smaller air velocities, so the pulse jet backhouse can use higher velocities. That will handle higher velocity, use reduced class area, right? But it requires some mechanical properties. But still, for the pulse jet backhouse, you need to consider the extra volume because it's quite easy to damage these materials, right? So you always need to consider one extra compartment so that when it's offline, all the other remaining compartments can still handle the airflow there, okay? So that's all for the contents of this class. I realized that I may be going too quick this time. So maybe we can spend some time to talk about the plan for our next week, right? So next week, on Monday, you will basically go through another online video. That's from Dr. Lindsay Marr on the COVID-19, okay? So last class, you probably know that we can use a lot of these aerosol concepts to try to understand how the particles, how the respiratory droplets move in the air, right? What is the exposure risk? So in our next class, we're also going to basically go through her remaining lectures about the functionality of the masks. How do we evaluate the performance of the mask? But basically, the masks are filters, right? So we're trying to get rid of the particles by capturing all of these particles through the future media. So I hope that that will give you a more understanding of how this class might be helpful in trying to understand this COVID-19 pandemic here. So after next class, I'll spend some time to briefly talk about the cost analysis for all the PM removal devices that we talked about. So we can also go through some other relatively not frequently being used PM removal devices. For example, the wet scrubber. So the wet scrubber is basically a combination of the cyclones and a water sprayer. Okay, so it can achieve a little bit better particle capture efficiency compared to the cyclones, but they're generally more expensive than the cyclones. So we can talk about that mechanism, and on Friday we will go through your homework problems. I'll return all the graded homeworks to you so that you can use that to prepare for the midterm. So we'll also go through a review session on our next Friday's class. So we'll have the exam on the week after, and then during that week you won't have homeworks, and you also take one class off. So just to relax a little bit, because we have been quite intense, I would say, going through all of these concepts on particles and all the concepts on different particle removal devices. So I would say that the midterm exam will mainly focus on PM, right? So we didn't talk about too much on the other air pollutants. So it's mainly just naming the 6 criteria air pollutants. We spent quite a lot of time on the ideal gas law for unit conversion, but most of the contents will be on particulate matter. For example, the drag force, right? So I think I reiterated quite many times that the equation that you have to memorize for this class, that's 3 pi mu dp divided by c multiplied by the relative velocity to calculate the drag force. So we mentioned, we introduced the gravity settler, or the settling chamber, which remove particles by gravity settling. We talked about the cyclones, the ESP, and now the Backhouse filters. So for each of the PM removal device, you need to know what is the mechanism and also what is the design criteria for these systems. Okay, so we can probably go through everything during our review session next week. But for this week, I think the homework is still mainly focused on design of the Backhouse filters, so you can get more practice on that. So I think that's all for this class. Just let me know if you have any questions. Let's say, typically if you email me, I'll respond pretty fast. Okay, so that's all for this class. You guys have a nice weekend.